Hi guys, welcome to our channel. So today's session we are going to discuss about 8086 architecture. Okay. The previous session we discussed about the 8086 pin configuration. So what are the functions we performed in the 8086 microprocessor. Okay. Now we go to discuss about the 8086 architecture. It's a basic building diagram of architecture. So in this architecture is split in two blocks. Okay. The first block is BAU unit, second block is EU. So what is BAU? So BAU stands for bus interface unit. So in this part only concentrating the interfacing. Okay. So how to interface the memory unit with the execution unit. So it's a main function of the BAU unit. The second unit is EU. So EU stands for execution unit. Okay. So in this particular block it involving the execution. Okay. Suppose the microprocessor is performing in arithmetic function and also logical function. Okay. The performing in the ALU unit, arithmetic function and also logical functions. Okay. So we will discuss one by one. The first block is memory interface. So it's a memory unit. In this memory unit you can store the codes and data. So in this block it stores the program and also data. So it's a main memory. So in this memory you can store the program value and also data. If you want to access the program, you accessing the program, or otherwise if you want to data, you send the memory location, so memory address, and then you can get the data from the main memory. Okay. So it's a dedicated adder. So in this BAU unit you can use the dedicated adder. What is the purpose of this adder? So in this microprocessor we need a 20 bit of address location to access the memory unit. Okay. So in this processor internal block only generating the 16 bit of address location. For example, here we are using the 4 segments: extra segment, core segment, stack segment and data segment. Okay. So these 4 segments are generating a 16 bit of value. So this 16 bit of value is converted to 20 bit of address location. Okay. So in this block is used to find the physical address. So in this block is used to find the physical address of memory. So once you find the physical address, after that you can get the program. So program or data. First you find the physical address. So what is physical address? So physical address is equal to segment address plus logical address or offset. So physical address equal to segment address plus logical address or offset address. The segment address you can get from the segments. So extra segment, core segment, stack segment and data segment. The logical address you can get from the source index, destination index, base pointer and stack pointer, then IP. So based on the information requirement, you can combine the segment register and also base pointer or source index register. That we'll discuss now. Okay. So it's a dedicated adder. So this adder is mainly used to convert the physical address. Okay. Now we discuss about the segment register. So one by one. So here we are using 4 segments. The ES stands for extra segment, CS for core segment, SS stack segment, DS data segment. Okay. So this extra segment is mainly used to store the data. Suppose you want to performing any functions, the future data will be stored in the extra segment. Then the code segment. The code segment is mainly used to store the program relevant content. Okay. Suppose you want to store the program relevant content, you can choose the code segment register. Just you can access the code from code segment. The next level of segment is stack segment. So this segment register is used to store the stack relevant content. Okay. Suppose you want to access the stack information. First you find the stack segment content, then you add with the stack pointer content. Just adding the two values, you can get the 20 bit of physical address, then only you can get the address memory data. Then next one is a data segment. So this segment is used to store the data values. Okay, suppose you want to access the data from the main memory, you can combine the data segment plus source and destination index register. Along with this register, you can convert the 20 bit of values. Okay, so now suppose you want to get the code segment value. So code segment is stored in a 16-bit address location. So this 16-bit address location is converted to the 20-bit of address location. First, you shift the value in 4 times left direction. So left direction. Okay, so after shift the 4 times of this code segment value, you can get the 20 bit of address location. So this 20 bit of address location is summed with the instruction pointer. Okay, so code segment plus IP equal to physical address. Okay, so the physical address value equal to code segment value. So whatever value present in the 20 bit of value, so the 20 bit of values you write here. Then instruction pointer value, the 16 bit of value, just adding the two values, you can get new physical address. Okay, so in this address location, whatever content is present, the content is transferred to the code segment. So it's a function of this segment register. So likewise, you can choose the extra segment and stack segment and data segment. Just you set the combinations of the index point and stack pointer and base pointer register. Suppose you access the stack segment, so physical address equal to stack segment plus SP. So whatever value present in stack segment, that value is shifted 4 times. Then stack pointer value, just you access, just adding the two register content plus you can get the physical address. Okay, so likewise you can fix it. Suppose you access the data segment, so DS plus SI over DI over displacement. Okay, so suppose you want to access the data segment value, just you adding the data segment value plus source index, or otherwise data segment plus DI destination index, or otherwise data segment is plus displacement. So what is displacement? So displacement is immediate values. So immediate values or some other instruction we can pass the label name. Okay, so just you adding the content, you can get the 20 bit of physical address, then you can access the memory unit. Suppose the extra segment means extra segment plus DI. So only here involving the destination index register. So just adding the two content, you can get the 20 bit of address location. Okay, so it's a basic function of the segment register. The next block is instruction queue. So in this 8086 microprocessor, here we are using one new block. So it's an instruction queue. Okay. So what is the purpose of this instruction queue? Just this instruction queue is prefetching the instructions from the memory unit. Okay. The memory unit is store the whole instruction, whole program code. Okay. So the code is sent to the instruction queue. Here, so in this block is get the 6 byte of instruction. Okay, so each instruction containing the byte, so 1 byte of instruction, 8 bit of instruction. So here you can access the 6 instructions. Okay, the basic function of this instruction queue is FI, FO. So first in, first out. Okay, so you can access the instruction from the memory unit. You just insert the instructions in the order. First instruction place here, second, third, fourth, 5, 6. So 6 level of instruction you can prefetch into memory unit. Okay. So after prefetching the instruction, the first instruction is passed to the control system. So what is control system? So control system is nothing but decoding unit. So it's a decoding unit. So this instruction is a human understandable language. So this human understandable language is converted to the machine level language. Okay. So in this control system block is converting the machine level language. So first you fetch the first level of instruction. So this instruction is passed to the control system. So after decoding, this block is sent to the control signal to the entire execution block. Okay, so in this particular portion we can fetch the instruction. Okay, so it's a interfacing. So interfacing with the memory unit. So in this particular block there are no functions execute. So addition function or logical functions. Okay, suppose you want to execute any functions, you go with this block. You transfer the informations to this block. Okay, so in execution unit the first block is control system. So what is the use of control system? Here decoding the instruction. So whatever instruction stored in instruction queue, that instruction is fetched and decode. Okay, so after decoding, that level of signal is transferred to the internal structure of execution unit through the A bus. So this A bus is carrying the control signal and also data transfer. Okay, then one by one you can fetch the instruction. So first instruction is move to the control system. The next level of instruction, all the instructions come to down to the one level. The new instruction again fetch from the memory unit. That instruction is placed in the 6th place. Likewise, it perform. Okay. So then the control system is converting the decoding. So machine level language, that signal is passed to the entire block. So next, so these all the registers are called as general purpose register. Okay, so these are the general purpose register. Here we are using a number of registers. Okay, so these 4 registers are used to 16-bit register or otherwise 8-bit register. Okay, so it's namely called as AX, BX, CX and DX. So this X represent the 16-bit value. So this A represent for the accumulator. This function is same to 8085 microprocessor. So in accumulator, just storing the content and also store the result. Okay, so it's a 16-bit register. If you want to performing any 8-bit addition function, means you just using the 8-bit register. For example, AL and BL. Just adding the 2 8-bit content and final result is stored in a AL register. Suppose you want to performing the 16-bit addition function. So here there is some provision to performing the direct 16-bit functions. Okay, so AX and BX, just adding the 2 content AX and BX, the final result is stored in the AX register. Okay, whatever you want to performing the 8-bit register, so 8-bit function you can choose AH or AL. Suppose you want to perform the 16-bit value, means you can choose AX and BX. So AX represent for the accumulator, just storing the 16-bit content and also it store the result also. Then the next register BX. So BX is a base register. Okay, so this register is similar to the 8085 HL register. So what is the use of HL register? Just storing the data. So just storing the data and also store the result. Okay, the third register is CX register. The CX register, so CX represent for count register. So this register is mainly used for storing the count values. Okay, suppose you want to use some shift function. So shift and rotate. Okay, then loop. So these 3 functions are fixed in multiple time. Okay, suppose you want to shift the content in 4 times. Suppose you want to rotate a content in 5 times. Suppose the particular function, that loop, is rotated in 4 times or 5 times, the iterations. Okay, the number of iterations is stored in a CX register. The CX register is namely called a count register. Just count the values. So count the iterations. The next next register is DX. So DX register is a data register. Okay, so it store the data. So it store the result. Okay, suppose we want to performing the addition function and subtraction function. The result is only 16-bit. So only 16-bit of result is produced. Suppose any overflow I get, that overflow is a 1 bit. So 1 bit overflow, that overflow is stored in a carry register. Suppose multiplexer and division function. Okay, so in multiplication function, you multiply two 16-bit numbers. The final result is 32-bit. Okay, so two 16-bit values you can multiply. The final result output is 32-bit of values it produced. The lower 16-bit value is transferred to AX register. The upper 16-bit value transferred to DX register. The DX register is a data register. This register is stored the upper 16-bit result of multiplication. Okay. Likewise, you can perform the division function. So in this division function, you can produce the two output, quotient and remainder. The remainder value is stored in DX register. The quotient is stored in AX register. So it's a function of DX register. The next one is stack pointer. So stack pointer also the same function of 8085. So it stores the stack pointer, address, location and also data. Okay. So this register is along with use the stack segment. Suppose you want to access the stack segment, memory location, memory data means you work along with stack pointer and stack segment. Then BP. So BP for base point register. Okay. So it's also one type of register is storing the data. The next one is source index and destination index. So these two registers are mainly used for the stack segment. So accessing the data segment. So accessing the data segment content, the data segment plus SI or DE, just getting the physical address. So offset address from source index and destination index. And also, so these two registers are used to move the block of data. So two block of data. So source point to destination point. So whatever value present in source point, so the whole value is transferred to destination point. So that and all we discussed in instruction format and address signals. Okay. The next block is ALU. So ALU is a arithmetic and logical unit. Okay. So whatever instruction you can fetch from the instruction queue, that instruction is passed to the control block. So here decoding the function, then this signal is passed to the entire execution unit. Okay. Suppose you want to perform in the addition function, you need two data. The two data you get from the specified instruction registers. For example, here I get the values from AX and BX. Okay. So the AX value is transferred to ALU unit, then BX value is moved to ALU unit. Just adding the two contents. So AX plus BX. Okay. So AX value plus BX value. So after addition, whatever value present in the ALU unit, that value again passed to AX through the bus. So through the bus. Again it passed to the accumulator. Okay. Then here using the flag register. Okay. So what is the usage of flag register? It's mainly used to check the status of ALU. Okay. So after execution of this ALU output, so what is the status of result? Whether the status of result is positive value or negative value, or all the values are 0, or otherwise the result is odd parity or even parity. Okay. Likewise you can check the status. Okay. So here the flag register is classified into two types. Okay. So two types of flag register here using. First flag register is conditional, second one is status. So this status flag register already we discussed in a 8085 microprocessor. So here the only one flag status only changed. So it's additional. So overflow flag. So in this overflow flag is not present in the 8085 microprocessor, but the 8086 microprocessor, the overflow content also included. Okay. The first we discussed the conditional flag register. So in this conditional flag register, we are using the three type of flags. You can check the three status. Okay. The first one is DF. So DF for directional flag. So in this flag is mainly involving in the string functions. Okay. Suppose the string function decrement the data or increment the data. The flow of direction, top to bottom or bottom to top, that will check in a DF. The next one is TF. So TF for trap flag or single step. So trap flag or single step. So this trap flag is always set to be 1. So because all the instructions. So instruction fetched one by one. So first instruction decode, then execute. Okay, so it's also considered as a one type of software interrupt. Okay, so the trap flag always 1. The next one is interrupt flag. Suppose the microprocessor is serve any interrupt, any peripheral devices. So in this case, it indicate interrupt flag. So interrupt flag value equal to 1. So any one of the interrupt is occur, the microprocessor is provide the service that will indicate. The next one is status. So in this status, here we are using the 6 status. The first one is sign flag. Okay, so whether the result is positive value or negative value. Okay, that will check in the sign flag. The next one is auxiliary flag. So auxiliary flag already I told in 8085 microprocessor, the middle of the bit. So middle of the bit, any overflow occur. So middle of the bit, any overflow occur, that's called as a auxiliary flag. Here the microprocessor maximum data width is 16. So 8. In the 8th bit, any overflow occur, so it's called as a auxiliary carry. Then carry. So carry flag is a end of the bit. End of the bit. Any overflow occur, so it's called as carry bit. Z represent for 0 flag. All the results, so after addition function or subtraction function, the result, all the bits are set to 0. In this case, 0 flag set to be 1. Then P. So P represent for parity. Whether the result is odd numbers of 1 present or even numbers of 1. That will check through the parity flag. The next one is OF. So OF for overflow. Okay, the range of result is exceed. For example, I am doing 2 8-bit number multiplication. The result is it produces 16 bit of values. It's not a result, it's a 16 bit of values. Okay, but input range is 8-bit, but output range is 16-bit. It exceeds the input range. So it's called as a overflow. Here the 8-bit is exceed compared to the input values. So it's indicating overflow. So this overflow flag only set in multiplication and division function, not addition and subtraction function. Okay. So it's a function of 8086 architecture. So next video we discussed in flag register structures, that we'll discuss in deeply. Okay. So thanks for watching my channel. Please subscribe.